Okay, product of powers. That's the first property that we're going to talk about. Product of powers is when we have something like a to the x times a to the y. What do I do with those two exponents? I add them, okay? Now, my base is the same. My base is a, okay? This only works if my base is the same. So what I'm doing here is I am adding. I add them. An example of this would be x squared times x to the third. That's going to be x to the fifth. Okay? So I add the exponents. I have to have the same base. That's super important that you realize that you've got the same base. Quotient of powers is when I have something similar to a to the x over a to the y. What do I do with those exponents? Subtract. Okay? So I have something like a to the x minus y, and my key word is subtract. Subtract. Okay? So if I had x to the fifth over x to the third, I'm left with x squared. I subtract. Okay. Power of product. Power of product. That is when I have something like a times b raised to the x power. Okay? Students like to call this the distributive property. This is not the distributive property. Okay? So just be aware this is not the distributive property. But students often think of it, and it works similar to the distributive property. You have to give that exponent of x to everything that's being multiplied together. So I'm going to have a to the x times b to the x. Okay? Now, where students get confused is when I have a number inside the parentheses. So I have 2x to the third power. That 3 belongs to the 2, and it belongs to the x. So that is 8x to the third. Okay? And students, for some reason, they just don't want to give it to the number. I don't know why, but that's where the mistake is. They write 2x to the third. Power of a quotient is similar. We are giving that exponent to everything inside that parentheses. So this is going to be a to the x over b to the x. And again, if I have a number, students are less likely to give the exponent to that number. So it should be x to the third over 2 to the third, which is x to the third over 8. So both of these right here, power of a product, power of a quotient, you give the exponent to everything inside the parentheses. Okay? This is not the distributive property, but students think about it like the distributive property. That exponent belongs to everything inside those parentheses. Okay? But it is not defined as a distributive property. It's defined as exponent properties or exponent rules. Okay? Specifically, power of a product and power of a quotient. Okay. Power to a power is when I have an exponent raised to another exponent. So I have a to the x, and that a to the x is raised to the y. What do I do with x and y? Multiply. So our key word here is multiply. Okay? So this is going to be a to the x times y. So if I have x squared raised to the 5th power, that's x times 5, or it's x raised to the 2 times 5, or x to the 10th. Okay? 0 exponent. When I raise something to the 0 power, what do I get? 1. Okay. So here, anything raised to the 0 power is 1. Anything raised to the 0 power is 1. So a to the 0 power is equal to 1. Now, I want you to look at negative x to the 0 power and negative x to the 0 power. Okay? These are two different answers. Okay? What does negative x without the parentheses raised to the 0 power give me? It is. It's negative 1. So that negative is not raised to the 0 power in my first example. Okay? The only thing that's being raised to the 0 power is the x. You can think of this as negative 1 x to the 0 power, so it's negative 1. In my second example, I have negative x inside parentheses. So that 0 belongs to the negative and it belongs to the x. So this is 1. You have to be careful there. You have to ask yourself, what is being raised to this exponent? That's what you have to ask yourself. Okay? Negative exponents. Negative exponents. So if I have a to the negative x, what does that mean? Fraction. It does. It's a reciprocal. So the a goes to the denominator. And what is that a raised to in the denominator? X. Okay? So these are reciprocals. That's our key word right there. Reciprocal. Okay? You move it to the denominator. So if I have 2 to the negative 3rd power, that's the same thing as 1 over 2 to the 3rd power, which is 1 over 8. 1 over 8. Okay? Now, I want you to be aware that very often these three properties, you do it all at the same time. Okay? Sometimes you've got things multiplied together and then things are divided and then everything is raised to another exponent. So it's not unusual for that to happen. So be aware of that. Be aware of that. Rational exponents I want to do on the next page, just because I want to make sure that we've got that. Can I move off this screen? Okay. Rational exponents are when an exponent is written as a fraction. When an exponent is written as a fraction. So look at this right here. Your top number, I keep saying I'm going to get my my Apple Pencil fixed. I mean, one day it's just going to quit. I have to get, and I know I've got new tips somewhere. I just can't find them. I looked all in my office this morning. Oh, no. Oh, dear. Is today going to be the day? I know. I even had an Amazon order. Oh, no. I guess anybody has an Apple Pencil, do they?
I have a pencil, but it's not an Apple Pencil, and you have to wear the glove.
Is it in your bag?
Yes. It automatically connects.
Give me 1 more minute. Let me see if I can get this fixed. I don't think I can do all this with my finger. I could try. I've been able to get it fixed. Well, now I've just, oh man. I really have, it's been giving me fits for more than a week.
Yeah.
Okay. It is not happening. I just write so big. I write big with the Apple Pencil. I can't imagine how big I'm going to write. Okay. Can I try it? Okay, you guys can run to the restroom, get a drink of water. Be back in 5 minutes. Okay.
Like this. And then it should just automatically. It's cool as heck.
No, you're good. Thank you so much.
So what do I do?
You just put these 2 fingers in it. Yeah.
Cherry?
And now it won't catch your hand.
Thank you so much.
Oh,
It's good as heck. It's only $20.
wow.
Yeah.
I need to get one of these as a backup.
Yeah.
Okay.
I got one.
The day has been saved. Woohoo! And I promise I'll order the tip. I said that people could go to the bathroom and get some water, so I know I had some people leave, so. Thank you so much. Thank you so much.
Oh, I got one for it.
Oh, you did? Okay, well, cool.
You gonna fix that?
I might. I don't know. I really just don't know. Should be on her way down.
It is. Let me fix that. Yeah. C over D. Is that better? When did the 5 minutes start?
That's a fantastic question.
Yeah, I'm going to say 3 more minutes.
That's not problem.
Are you talking about that pen? Yes. Is that what you're saying? $20. Well, I've had that pencil. It's been a hot minute.
Have you heard of the
Maybe 4 years.
Wow.
Have you heard of the Logitech crayon? That's cool.
Is it cool?
Yeah, it has the same internal stuff as an Apple Pencil, but it's a different shape.
Okay.
It's really cool.
Years and years ago, when I very, very first started teaching online,
Oh, give me that.
I had a walk contact. This is it was after 2008. And it was just a block. And you couldn't see it, but it would show up on your screen. And that was the coolest thing. I paid $100 for it. It had to be, plugged into my computer. But it was cool. I was ahead of the game because I could do videos on my walk-on tablet. And then it just went downhill. But I have had it for a long time, so I'm not surprised I need to replace the tip. I'm just surprised that I don't know where the tip is.
That one is you don't have to replace.
20 bucks.
And it automatically connects. I didn't have to.
Now do you have to charge it?
Yeah, it comes with a little charger and it uses it. But I haven't charged it since I got it, and that was like a month or two ago.
That's cool. Very cool.
You like it? It's flashing. I'm flash. I did. I made it myself. Thank you. It was a lot of hard work and dedication. All right, I'm ready.
You think it's been 5 minutes? It's been pretty close. Okay. Rational exponents. Rational exponents are when your exponent looks like a fraction. Okay? And you translate that into your numerator going inside the radical. So that is going to be the numerator with your fraction, of your fraction, okay? Then your denominator goes here. That is the index with your radical sign. So that is your denominator. Okay, so that is how rational expressions work. So here I've got x to the 2/3. X to the 2/3. My numerator goes inside the radical, so that's x squared. My denominator is the index of my radical. So you read that as the cubed root of x squared. The cubed root of x squared. 1/2 is your most famous rational exponent, and what the 1/2 means is the square root of y. That's what the 1/2 means. Okay? So let's look at some of these. 64 to the 1/2. What that means is 64 to the first power, and you don't have to write that first power, the square root. So the 1 is assumed with the 64, and the 2 is assumed anytime that you've got a radical. So you don't have to write the 2 there. You can write this as the square root of 64. What is the square root of 64? 8. Okay? Now, 8 to the 2/3, that means 8 squared. You do have to write that squared because it's not assumed. The only time you don't have to write it is when it's 1/2. And I am taking the cubed root of x squared. X squared is 64. And I can take the cubed root of 64. What is the cubed root of 64? Does anybody know what it is? It is 4. 4 times 4 is 16. Times 4 again is 64. And so this simplified is 4. Okay? 9 to the 1/2, that is square root. Anything to the 1/2 is just a square root. Square root of 9 is 3. Okay? Now we're going to review a little bit more. We're going to review negative exponents, and then we're going to have some rational mixed in. Can I move off this screen? Okay. 5 to the negative 2. 5 to the negative 2. What that means is 1 over 5 squared. Notice that the negative exponent does not make it negative. Now, sometimes we have negative numbers when we're dealing with exponents, but if you've got a negative exponent, that doesn't mean the number's negative. It could be, but it doesn't mean it is. And in this situation, it's not. So this simplifies to 1 over 25. Okay? Now I've got the negative exponent in the denominator. When I have a negative exponent in the denominator, what I do is I move it to the numerator. Okay? So the first one, I had a negative exponent in the numerator, and I moved it to the denominator. Now I've got it in the denominator, and I'm going to move it to the numerator. Okay? So this is going to be 7 squared over 1. Okay? I don't have to write it over 1, but I can. And what is this? What's 7 squared? Good. It's 49. Okay. Now I have 27 raised to the negative 1/3. 27 raised to the negative 1/3. I'm going to deal with the negative first. I'm going to deal with the negative first. So I'm going to move this to the denominator, and then I'm going to have 1 over 27 to the 1/3. Okay? So in the denominator, that becomes 27 to the first power, and I know that you don't have to write that the 1, okay, but a lot of times I do. Then we've got to have our cubed root right there. Okay, what is the cubed root of 27? 3. Okay? Okay. So these are just to get your mind remembering how to do exponents. Remembering how to do exponents. Now we are going to look at the graph of some exponents. Okay, we're going to look at the graph of exponents. So grab Desmos. Grab Desmos. You guys have Desmos? Okay. We're going to look at this red graph first. My red graph is f of x equals 2 to the x power. You can see the red right here. That's what's happening right there. That's my parent function. Remember we talked about parent functions way at the beginning of the semester? 2 to the x is my parent function here. Now, what I want to do is I want to plug in some numbers for that. So, the first number I'm going to plug in is 0. So, I have 2 to the 0 power. What's 2 to the 0 power? 1. 2 to the 0 power is 1. Okay? Now I'm going to plug 1 in. So, I have 2 to the first power. What's 2 to the first power? What is it? 2. Then I'm going to plug in 2. So I have 2 to the second power. What's 2 to the second power? 4. Okay. So here is 2 to the 0 power. Here is 2 to the first power. Here is 2 to the second power. Okay. Now I want to plug in negative 1. What is 2 to the negative 1 power? 1/2. Okay. What about 2 to the negative 2 power? And 2 to the negative, whoa, okay. Okay, here we go. 1/4. Okay, what about 2 to the negative 3rd? 1/8. Okay, so now I want us to talk about what's happening as we approach infinity with our negative numbers. Negative 1, negative 2, negative 3. What is happening to my fraction here? It's approaching 0. Does it ever touch 0? No, okay? So this red line right here keeps going and going and going. It gets closer and closer and closer to 0, but it never hits it. It's just approaching 0. So for my red graph, I have a horizontal asymptote right here. Okay? It's y equals 0. That is my horizontal asymptote. Now, I have this point of 0, 1. This point right here, 0, 1. That is on every parent function, because anything raised to the 0 power is 1. That is an incredibly important point when you start talking about translating functions and we start moving them around. Because with exponents, it doesn't matter if you've got 2 to the x, if you've got 3 to the x, if you've got e to the x, doesn't matter what you have. When you raise that to 0, what are you going to get? 1. Okay? So you need to pay special attention to what's happening to that point 0, 1. Okay? You need to pay attention to that. So, let's look at this. Let's look at our blue one. I have f of x equals 2 to the x plus 1. When I have something inside the parentheses with the x, is it true to value or opposite to value? Okay? Think about translating functions. Think about translating functions. If I have x squared as my parent function, and then inside parentheses I have x plus 2 squared, where did that parabola go? Up, down, left, right? It went to the left, too, because it's opposite in value. So I want you to look at this blue right here. Here's my parent function right here. There's that point. That's my parent function. My blue function is moving to the left 2 spaces. Oh, no, not 2. 1 space. It's moving to the left 1. Okay, look, that point moved right here. Okay? You want to know where that point 0, 1 is going. You want to know where it's going. What's my asymptote for this blue graph? Did my asymptote change? No. So my asymptote here is still y equals 0. Now I want us to look at the green graph. Okay? The green graph. What does the negative 3 mean? F of x equals 2 to the x minus 3. What does the minus 3 mean? It's going to shift down 3. Okay, now I want you to look carefully right here. Here's that red point is my parent function, and I always want to know where that red point's going. Okay, so this red point has gone down 3 spots, but where is it? Where is that point? 0 what? It's not negative 3. It's negative 2. And students really, really want it to be negative 3. But it's not, because where did it start? It started at 1. So this point right here is moving down 3. Okay? Now, my red function had a horizontal asymptote at y equals 0. What has happened to that horizontal asymptote? It has moved down 3. So it approaches y equals negative 3, but it never crosses y equals negative 3. Okay? So my asymptote is y equals negative 3, and my parent function went down 3. So what you're going to ask yourself when you're looking at this, you're going to ask yourself 2 things. First thing that you're going to ask yourself is what happened to the point 0, 1. Okay? Because you want to know what happened to that point, 0, 1. You want to know. The second thing that you want to know is, did my horizontal asymptote move? So those are the things that you're asking yourself when we are talking about translating functions. Okay? Can I move to the next screen? This is a decent thing to take a picture of if you didn't write it all down. Decent thing to take a picture of. Do you like all the pretty colors? Okay. Can I go to the next screen? Okay. I'm still dealing with a parent function of 2 to the x. So that's my parent function. Okay. My blue function, the negative is with the x inside the parentheses. So when the negative is inside the x, inside parentheses, what did I reflect across? What did I reflect across? Look at my blue function to my red function. Did I reflect across the x-axis or the y-axis? The y. So when my negative is inside the parentheses and part of the exponent, I reflect across y. Okay. Now, the green graph, I've got a negative in front of my base. Now, the negative is not part of my base. The negative is not being raised to the exponent. The negative is just in front of it. Okay? What happens when the negative is in front of my base? I reflect across the x-axis. Okay. I reflect across the x-axis. Now, I want you to look at this point right here. That's my parent function point. And then I want you to look at this point right here. Okay? My parent function's point of 0, positive 1, what did it become? 0, negative 1. It became 0, negative 1. Okay? So you have to pay attention to that. You have to look at that. You're always going to do the reflection across the y-axis or the x-axis first. Okay? Now, what is my horizontal asymptote to my green? What's my horizontal asymptote? It's still y equals 0. It's just underneath it instead of above it. For my blue function, my horizontal asymptote is still y equals 0. Now, what I want you to think about before we go on to our next problem is I want you to reflect across reflect across x-axis first. Okay, so you're going to do your reflection first, then you're going to do your movement. You're going to do your reflection first, then you're going to do your movement. Okay? Can I go to the next screen? Anybody want pictures of that before I move it? Okay. E is just a base. E is just a base. So what you've got is negative e to the x plus 3 minus 4. I want you to take about 1 minute, long enough for me to go refill my water bottle, to answer these two questions. What is the parent function? What is the movement of the graph? It's okay to use doceri. It's okay to use doceri. Okay, we're going to get started. What's my parent function? What's my parent function? What's the base? It's e. Yeah, my parent function is e to the x. Okay, so I have f of x equals e to the x power. Now, e is going to be something that we deal with. We're going to talk about natural logs. E is used. Do I have any biology majors in here? Any biology? Okay. E is used a lot when you're talking about growth models for bacteria or decay models for like asymptotes. Isotopes. It's not asymptotes. Something like that. Okay? Decay models. It's used in population growth. It's also used in bank accounts for compounded continuously. So E is a model that's used quite a bit. Now, what is the parent graph doing? Where all is the parent graph going? Okay, it reflects across the y. That's the first thing it does. Reflects across y. Then what? Moves to the, how many? So it moves to the left 3 because of that x plus 3. Remember, when it's with the x value, it's opposite. It's opposite. That's why it's moving to the left, because of the x plus 3. Then what happens? Good. Down 4. Okay? So let's see if this is what happened. Can I go to the next screen? Okay. So, the red is my parent function. There's my parent function right there. Okay. That point is going to get reflected across the y-axis, or the x-axis. I'm sorry. Yes?
Yeah, I was going to say, you said that it reflected across the y, but it reflects across the x.
That I messed up. It reflects across the x-axis. I'm sorry. Thank you, Lindsay. Thank you very much. Okay, it reflects across the x-axis. Okay, and here is where that point is. When I reflect it across the x-axis, I have to think about that, make sure I say it right. That's where it ends up. Then I am moving this point to the left. 1, 2, 3. Then I am moving down 1, 2, 3, 4. So there is that point. That's what's happening to that graph. Now, you will be asked to do stuff like this on your project. Okay? You're not asked to do this detailed on the test. There may be a little bit, but not this much. This is something that you'll be asked to do on the project. Okay? Can I go to the next screen? Okay, what we're going to do here is we are going to look at really simplifying some more intense exponents, so exponents on steroids, but we're still going to use those same properties. So this is 3 to the 2x plus 1 over 3 to the x plus 3. My bases are the same, so what do I have to do with my exponents? Subtract them. So I have 3, and then I have 2x plus 1 okay, and then I am subtracting the denominator. So I have x plus 3. Where do you think students make mistakes? They forget to distribute that negative. You're absolutely right. That's where students make mistakes. So this is 3 to the 2x plus 1 minus x minus 3. Okay? Then I combine like terms, and I'm left with x minus 2. Okay? So I used the properties of exponents. I just have more inside the exponent that I'm dealing with. Okay? Here, I've got the product of powers. I have 6 to the 3 raised to the power 3y times 6 raised to the power negative 4y. Okay? I add those exponents. The bases are the same, and they're being multiplied together, so I add their exponents. So I have 6 to the 3y plus negative 4y. Okay? So that's 6 to the what? Negative y. Okay? So then I can rewrite that as 1 over 6y. Yes?
So do you just leave the actual numbers alone and not multiply them together either?
Correct, because they are the same base. Most of the time what you're dealing with, that's a great question, okay? Very often those will be x's or y's or something like that. So you do not multiply the base together when you are doing the exponent rules. Excellent question. Excellent, excellent question. Okay? Yes?
That applies to everything, right? Not just this. But if you have a number for this one over here, you wouldn't divide by 3 and 3.
You would not. We're doing a very specific exponent rule right here. If we had something like 2x to the third over 4x to the first, okay, you would divide 2 and 4. Like you would simplify 2 and 4 in this situation because we're not dealing with exponents there. Okay, the x to the third and the x to the first, that's what we're dealing with the exponent rules. So your base for this situation is your x. It's not the 2 and the 4. When your number is the base that you're dealing with, that's when you do not multiply it and you do not divide it. When it's the base that you're messing with all the stuff. Okay, that's great questions, and I'm going to think about how to really explain that. Okay? Okay, now I've got one more, and then we're going to do some equations. This is a power to a power. What do I do when I am raising a power to a power? Okay, so I'm going to have 9 y to the third times y squared plus y. Okay? 9y to the third times y squared plus y. What do I do with that y to the third? Distribute. So I'm going to have 9 y to the fifth plus y to the Wouldn't be y to the third, would it? Oh, yeah, it would be y to the fourth. We're multiplying the y to the third times the y squared plus y. Okay? So we've got y to the third times y squared, which is y to the fifth, y to the third times y, which is y to the fourth. We're doing all sorts of different properties there. Okay. Now to the meat of what we want to be able to do with exponents. Question?
Would you add the y and y more?
No. Okay? You can't do that because they're unlike terms. If it was y to the fifth times y to the fourth, then you would add. Yeah. So, I mean, what happens is we get these different properties and we're trying to remember all of them.
So this is a simplified.
That is as simplified as it goes. It does not simplify any further. Good questions. Okay. This is the meat of everything right here that we're doing. Well, the graphing's pretty important too. Okay. If a to the x equals a to the y, then x is equal to y. If your bases are the same, your exponents are equal. What happens is, students remember the part that the exponents are equal, and they forget the part that the bases have to be the same. This only applies if your bases are the same. This is my base. Okay, if my bases are not the same, then the exponents are not equal. So here, I've got 3 to the x and 3 squared. My bases are the same, so that means my exponents are equal. Okay? Now, if you can use this property, you want to use this property. Okay? There is a way to solve these using logs where you don't have to use this property, but you want to reserve that for when this is not possible because it is more complex. And when we add complexity, we add more opportunity for error. So if you can use this property, you want to use this property. So let's look at how this property works. Here I have 7x squared plus x equals 7 to 4x minus 2. This equation has the same base. Okay? We have 7 here and we have 7 here. So that means x squared plus x is equal to 4x minus 2. Okay? And I can solve this. Okay, so I'm going to bring my 4x over. I think it's just me. There we go. So then I have x squared minus 3x equals negative 2. What's the next thing I do? Bring my 2 over. This hopefully is an incredibly straightforward factor. So I have x squared minus 3x plus 2 equals 0. Okay, what is this factor to? Okay. X minus 2, x minus 1. Okay. Negative 2 times negative 1 gives me positive 2. Negative 2 plus negative 1 gives me negative 3. So what are my two values for x? So x equals 1 and x equals 2. Now, I want you to get in the habit of checking. You've got to get in the habit of checking. When we do problems like this, especially once we move into logarithms, you are going to have extraneous solutions. And when you have extraneous solutions, sometimes you have to throw those out. So we have to go back and check. So I am going to check the 1. So I have 7 times 1 squared plus 1 equals 7 times 4 times 1 minus 2. So I get 7 to the second power and 7 to the second power. So it works. You could even go one step further and say 49 equals 49. Okay? Now I've got to do the second check, which is the 2. So I have 7, 2 squared plus 2 equals 7, 4 times 2 minus 2. So I get 7 to the 6th power and 7 to the 6th power. And that's going to be a pretty big number, so I'm not going to do that one. I'm not going to solve 7 to the 6th power. Okay? Can I go to the next one? Okay. 4 to the x squared minus 23 equals 16. What is the exponent with 16? What's that exponent? 1. Okay, students forget they've got to rewrite the 16. They want to do, oh, that's easy. X squared minus 23 equals 1. It does not. It doesn't work because my base is not the same. If you can rewrite it, you want to rewrite it. If you can rewrite your base, you want to. How can I rewrite 16? Good. 16 is 4 squared. Okay? So I can rewrite the 16 as 4 squared. Now, my bases are the same. My bases are the same. So I can write my exponents as equal to each other. So I have x squared minus 23 equals 2. I subtract 2 from each side, and I get x squared minus 25. That factors to what? Good. X plus 5. That's a difference of perfect squares. So x can be negative 5 or x can be positive 5. You have to check. You got to check. Okay? I have 4 and my negative 5 is being squared. What is negative 5 squared? 25. Students make mistakes right there. So be careful. 25 minus 23 is 4 squared. 4 squared is 16. Now I'm going to check the second one. 5 squared minus 23. Okay. 5 squared is 25. Minus 23 is 2. So we end up with 4 squared equals 16. And that works. Okay. If you can rewrite the base, you want to rewrite the base. Okay? It is more complex if you don't. So you want to get in the habit of doing that. Here's our last one. And this one is more complex because you have to rewrite both of them and then you have to do some of the property rules. I have 9 to the x plus 3 equals 27 to the x plus 6. Neither one of those are the same bases, and I cannot rewrite either one of them to get to the other one. Okay? But I can rewrite them in terms of 3. 9 is 3 squared. Now I am raising 3 squared to x plus 3. So I am raising a power to a power. Okay? What can 27 be rewritten as? 3 to the third. I am raising 3 to the third to x plus 6. So, students forget they've got to distribute. That's where they make the mistake. That 2 has got to be multiplied times that other power. So I've got 3 to the 2 times x plus 3. 3 to the 3 times x plus 6. Okay? Now that I've got my bases rewritten as the same base, I can use the rule that says my exponents are equal. So I have 2 x plus 3 equals 3 times x plus 6. So 2x plus 6 equals 3x plus 18. I'm going to subtract 3x from both sides. So I'm left with negative 1x equals, I'm going to go ahead and subtract negative 6 from both sides. So I get negative 1x equals positive 12. So what does x equal? X is negative 12. Okay, x is negative 12. I'm going back to my original equation to make sure it works. So I'm going to have 9 to the negative 12 plus 3 equals 27 to the negative 12 plus 6. I'm not able to tell if that works. I would either have to put that in a calculator and do 9 to the negative 9 and get a very, very small number, or I'm going to have to rewrite it again. We already know that 9 rewrites as 3 squared, and 27 rewrites as 3 to the third. Okay? 2 times negative 9 is negative 18. 3 times negative 6 is negative 18. Does it work? Yes. Okay? Okay.